right, hello. How's everybody doing? Hi, I'm Martin Robaszewski, and I'm going to be talking about developing a scalable render farm using Unity. So this is the agenda. I'm going to give you an overview of our game, Design Home, which is a mobile game. And I'll go through it. There'll be some videos. You'll see the gameplay, and I'll talk about a lot of the technical things that we have done with it. And then we'll go talking about the render server farm architecture. And then we'll talk about how we do over 2 million renders a day. And then there'll be a little post-mortem and QA if there's time. So Design Home, what is it? It's an interior design game that's on mobile. It's on iOS, Android, and Amazon. It has thousands of items from real-world brands. We announced last month we hit 1 million DAU. There's over 2 million designs. These are unique designs submitted every day. And we've had over 25 million downloads. So I'm going to play a little video. So the game loop is you have these design challenges. There's 5 a day. And you enter them, and you basically decorate a room. I will play the video. And it'll enter a challenge. The blue dots are required spawners, and then the purple ones are optional. So the game's going through. We're picking out items. And these are all real-world items. You can actually click on the eye icon, get a bigger image. You can actually go to the brand's website, purchase it if you want the real-world item. So we're filling it up with furniture. OK, and we're getting close to done. So I said there's 5 challenges a day. They're in different locations. They have different layouts. They have different requirements. There's a lot of combinations that you can have, and like this room has quite a bit of a lot of spawners. There's a lot of options for items per spawner that you could fill the room with. And here we go in and we submit it. I'll pause that for a second. So this render here is done on device. Basically, we just grab what you have there, and you can share that on social media. But also at this point, we send some data to our backend, and that kicks off the render server farm job to render it at a much higher res. And we'll talk about that later. So let that finish. OK, so I mentioned there are a lot of possibilities for design. So a very rough estimate, if you had a room with 10 spawners, 20 items per spawner, that's about how many combinations you can have. And actually, the number could vary. It could be a little bit lower. It could be a lot higher, depending on the challenge. There could be a lot more spawners. There could be less spawners. There could be restrictions. Sometimes there's restrictions like use a red sofa, which limits your choices. Sometimes there aren't. So there's a wide variety of rooms that we can get. So here's another video. And this one will show you a design history. This is actually my design history. So you can see the variety of rooms that I created and my scores that I got. So there's a voting process after you submit your design. There's a period when submission, there's a deadline, and then it goes into a 24-hour voting period where people vote. And at the end of that, you get your results, and you can get awards, in-game currency, in-game items, things like that. So that's, and like I said, that when things get submitted, they go to the render farm. So the main reason is when we get to voting, all the images are ready. And why do we need all the images ready? We're going to get into that. So here's some stats. We do 5 design challenges per day. There's usually one daily challenge, which has no restrictions, and then there's 4 regular challenges that have restrictions. And then those are like 3-day challenges, so you have 3 days to enter them. And then we also have, it's not listed here, we have sponsored challenges. We have HGTV branded challenges a couple times a week. And then we get 10 to 15 new items per day, so that every day we have new content rolling out. So we have a pretty massive build pipeline, and I'm going to talk about that in a little bit. And then we have currently over 6,000 items, over 2,000 challenges. So if we're doing, 2.2 million designs a day, in a year we're talking over 500 million designs by players. This is user-generated content. It's a lot of data, a lot of images. And like we said, voting period lasts for 24 hours once a design challenge has ended. So here's an example of our store that shows new arrivals. This is from last week. So these are new items that each day you could see. There's a selection of new items coming in. And these are all 3D models. All the data you get, unlike a typical game, you would maybe start it and it downloads a big blob of game data assets. We kind of download on demand. As you enter a challenge, we'll download that challenge data. As you select a new item, we'll download that item data and asset bundles with them. And we also have a system where we, depending on the level of device you have, we will download, if you have a lower end device, we'll download low resolution textures. If you have a higher end, you'll get the higher resolution textures. This way we can scale with the devices, the capabilities of the device. So the current asset bundle counts. So these are like rough estimates. Our challenges take about 8 asset bundles. We tear up our assets so we can actually have each texture is in a separate bundle. Because then we kind of, like I said, we load them on demand depending on the device. So our challenges, right now we're at like 16,000 asset bundles, and that's per platform. So you multiply it by 3, which is iOS, Android, and then our desktop, which is our render server farm. It's a lot of bundles. And then our items, even more, over 120,000 per platform. And how much does all that data, how much space does it all take up? So some rough estimates. This is on mobile, so the asset size on mobile would be, if you downloaded everything, this would be the download size. It may be a little bit bigger once it gets uncompressed. So we're talking about 20 gigabytes of data. So you can't, realistically have all that data on your device. That's why we download everything on demand, and that's why we have a need for this render server farm. So yeah, why did we need a render server farm? I mentioned the issue that user storage and bandwidth. Also, consistent image quality. Different devices have different rendering APIs. So by having one, render quality, everybody is going to be competing at the same level when they're being voted on. So the images that you see in voting, the images that you see, like you saw in my design history, those are all done on a render server, and we render them, we resize them, so we have them at multiple resolutions. So we only pull down what you need when you need it. And the farm is scalable with demand. As we need more, demand picks up, we spin up more instances. And then we also, we talked about the voting, so we queue up, we try to get the rendering done before voting. So when people go into voting, there's a nice experience without lag where they can just get the images immediately. There are times we have hiccups, and we do have fallbacks if somehow for an image didn't get rendered. There is a shortcut that's done, and it'll actually just serve up the image at the res you need, like on demand. It'll take a little bit extra time if the files aren't cached on the server, but we have that there. So here's a little voting video. And you can just see, so this is the same room, the same design challenge, done by different people. And I'm just going through and just kind of voting on some of them, and you can see the variety of designs that are being done. So when we get 2 million renders a day, they're pretty much unique designs, because those are requests to be rendered. If there's already a render with that design, it won't do it. So there is a chance that people would get the same render, but it's very rare. So let's go into the actual render server farm. So here's kind of like a high-level, very high-level view. We have the blue client, which is the game, the app. It basically, when you submit your design, it sends that request to the game server. It records your design in your history, your player record. It then generates a URL that goes through it. It actually, it gets more complicated than this. I really simplified it. It actually, sees if the file's on CDN. If it's not there, then it sends it to the render farm. It goes to the render farm, and then it gets pushed out to the CDN. So any future requests, like if you're looking, if you're going to voting or looking at your history or looking at someone else's history, you're actually hitting the CDN directly. And if it's, if the file's there, it'll grab it. If it's not there, then it'll do the shortcut and generate it on demand. So we're going to zoom in. Here. So let's kind of go into the client. Like I said, I kind of mentioned, I guess I already went through the flow. But what we also have is a version of the client is actually part of the render farm. So it's the same algorithm. It's the same engine, but it's running on a desktop. It's actually running on Linux. We do our development on OS X, and we actually do most of our testing there. And then we just deploy to Linux for the rendering. And then the game server, like I said, that translates the data to a URL. And it does a bunch of other things, like the queuing up, record management, things like that. And then it passes it to the render farm. And then that goes to the CDN. So we're going to zoom in to this part next. So here we have kind of like our render farm cluster. The first thing that it hits is a load balancer. And then there's multiple render instances. And these are physical machines that run the render server. So we can have, we probably have like right now maybe 20 machines running in a cluster. And then after that, once an image is rendered, it goes to the image resizer. So we're going to go into a render instance, and it's going to look a little familiar. It has another load balancer. So it actually has multiple containers. These are Docker images, Docker containers running images of the game, and basically allows us to run multiple copies of the game on the same physical machine. So the load balancer will, knows, hey, who's not busy? OK, I'm going to send it to you. Image gets generated, and then it goes back up the chain. So here's kind of like our tech stack that we're using. As mentioned, we do our development on OS X or OS X. We deploy the farm on Linux with the Linux player. We just build to it. We run on Amazon AWS EC2. It's all Docker, and I'll talk about that a little bit more next. We use Grafana for like our charts, which we'll see a little bit later. And then there's Supervisor D. That's kind of just watches the system. If there's hanging processes, it kills them, restarts them. And then HA proxy is our load balancer. So these are all things you could Google. You'll find them. It's a lot of it's open source online, which is pretty cool. So this is kind of like Docker. So Docker is basically like a virtualization system where you can run. They're called Docker images. They run as containers. So we actually have up to 5 running at one time on a physical machine. And then it makes it easier to deploy. There were some issues, which I'll talk about in the post-mortem. And we'll get to that a little bit later. So now, how do we get 2 million renders? So this is a 24-hour graph of like one full day, 24 hours of our usage and requests. And you could see, around 6 a.m., it goes up. Probably people wake up in the morning. There's challenges from the night before. They start entering them. Load goes up. And then you'll see another chart in a few slides that'll show you where we spin up extra instances to deal with that load. And that's why it levels off and goes back down. So if we do some reverse math, 2.2 million a day, that's about 91,000 renders an hour, 1,500 a minute, 25 a second. So you're talking about maybe 2 seconds a render. These are very rough numbers. So we would need about 13 render instances. So if we look here, you can see we have about 10 instances, the green line at the bottom. We have 10 instances till we hit that 6 a.m. time. Then we start spinning up more instances to help deal with the load. And then it levels off after a while. So we have, it's all part of like the monitoring setup. When CPU load goes too high or other latency gets too high, that's when we start spinning up new instances. So we have alerts that it's all automated based on parameters that we set to kind of keep everything running smoothly. So I mentioned, hey, we're at 2 million, but actually we go to 8 million because of our resizer. So we, after we render our 2K image, we then resize it to 4 smaller sizes. And this way, those are, if you're looking at someone's preview history, you'll be grabbing probably the 128 size. And then when you actually go in and look at the nice higher res, it'll pull down the higher res version of it. And as, like I said, it does that all on demand. So a little bit of a postmortem. Yeah. So I guess our first thing, our QA render server doesn't even use a CDN when we're testing. So it actually never caches anything. So it's actually getting hit directly. So if we have a bunch of QA testers hitting it, they're all, they're going to get queued up, and we can kind of test performance that way. Make sure we have error logs, because sometimes to figure out what went wrong, we have to go searching through them. So definitely log everything that you can. One thing we did was we were testing on prod, for about 3 months before we got our own QA instance. It was just limited resources to get everything up and running. But now we actually have 2 QA versions. We have Unity. We're still live on Unity 5.3 while our client is on 5.6, and we're testing a 5.6 render server. And hopefully, maybe by the end of the month, we'll roll that out. And it just to keep everything in line before we move up to the next higher level of Unity. And then our system also, for like our challenges, if there's, for some reason, it can't find an older version or some data's corrupt or something, it will try to roll back to a previous version and load that. Because we had issues with that. And then early on, our CDN syncing was kind of a manual process. We would, when a game starts up, it pulls down game data, which is kind of like metadata, so it knows about the challenges, it knows about the items, and that's updated daily. And there's a time where the CDN update, which is our content, the furniture items, the challenges, the backgrounds, the rooms, were manually updated. And they would get out of sync, stuff would get lost. So now we kind of couple them together, so whenever we push out game data to QA, we also update CDN, and then this way it's always up to date. There's still issues that slip by, so but sometimes it's more there's a build failure and something didn't get built properly. But we're trying to put processes in place to capture all that, to avoid it. And then so one of the biggest challenges was building out these headless Docker containers, because they're running X11, and they're sharing, you have 5 instances sharing this X11 server, and it's running on machines, without monitors and everything. So by default, like if there's no monitor, Unity starts up, it'll start up without any kind of rendering, and we need rendering. So that took a bit of trial and error. NVIDIA now has Docker support. If you search for NVIDIA Docker, they have like a GitHub repo, and it'll make your life a lot easier if you need rendering support. Because part of that issue was, if the Amazon image has a certain driver version, and then your image has to match that version. And that was, if they were to update their version, we would then need to update our image with newer drivers and things like that. So I think right now we're like forcing to stay on an older version until we get around to updating. Probably when we roll out the next 5.6 server, we'll update again. And that's about it. Any questions? If you have any questions, please come up to the mic. If not, I'll be available afterwards if you want to talk privately. Okay? All right, thank you.